Hello everyone, my name is Matthew Lucio and today I'll be presenting my senior research project in the Computer Systems Lab titled Marching Band Drill Analysis with Computer Vision. So a little bit about myself is that I'm a member of TJ's marching band and I've really enjoyed the experience. And I was thinking about how I could create a piece of software to evaluate the marching band's drill accuracy. That's what I decided to focus on for my senior research project. Now a little bit about what I'm going to be talking about in this presentation. I'll start with the background research necessary to understand the scope of this project, and then move on to talking about the Yolo 5 algorithm and how I use it to detect marchers and shapes they create on the field, commonly referred to as a drill. I'll move on to error correction software, which is basically how I calculated the horizontal positions of marchers on the field. And comparing this to the intended drill sheets can greatly improve a marching band's drill accuracy. Another important aspect of the drill component in marching band is the consistency of marchers moving between sets, which is the final part of this project, and then I'll wrap up everything, as well as talk about the applications of this project. So there was not much available background research for marching band computer vision projects. However, I did find some related to football fields as well as soccer players. But I think that's what's really neat about this project. Nothing like this has ever been done before, and I'm excited to show what I was able to produce. So the first important component is understanding YOLO, and it stands for You Only Look Once. And it's a real-time object detection software that draws boxes and classifies common objects in images and videos. And the way that this actually works is it uses a convolutional neural network which divides the images into grids of data and then trains it over hundreds and thousands of annotations on these example images to understand and locate common objects throughout these videos. And there are lots of different versions ranging from 1 to 5, but I began with YOLO version 3 because that seemed the easiest to begin with. However, I quickly upgraded to version 5 because there's a noticeable speed and accuracy improvement, especially when I completed annotations by hand on the RoboFlow software, which I will demonstrate and explain now. So this is what the RoboFlow program generally looks like, but here are some of the example annotations that I had to do by hand to recognize marchers as well as the shapes that they create. And RoboFlow also provides a health check, so if you're going to be doing a YOLO project, it is definitely important to understand how many of these annotations you might have to do by hand. And this will bring me into my first demonstration of my code. So I'll run this quick software here, but basically I created a Tkinter GUI which has lots of options for image transformations depending on what the user would like to know about a marching band drill. So I'm just using the shortcut keys and I've copied this video path, but I will show the YOLO version 3 example first here. Now, one tick of this progress bar that I implemented shows 1 frame of the video, and you can see that it's noticeably very slow, as well as has unnecessary labels for the images as well, which kind of get in the way of the image, which is improved on the YOLO version 5 video. So I'll just wait for this to complete and show a time lapse here until that process is done. Alright, we are finally done. Now you can click this show video button to actually see the final product in real time. Comparing to the YOLO version 5 algorithm, the process is much quicker and it finds a lot of these marchers in the back noticeably as well. So you can see the noticeable improvements from the newer version. And that is why I switched. Now from now on, I will just show the final video outputs because it is not really necessary to actually see the process. Now another application of YOLO comes into play with respect to shape recognition. Now I wanted to be able to find vertical lines of marchers in any image. And this requires Yolo to draw the boundary box in the video first before it performs 4 computer vision algorithm transformations in the form of a blur, then a grayscale, then a canny edge detector, and a Hofflein's P method. This is all in the OpenCV library using Python. However, these images show what each of them actually do. So here's an original frame of a video, and you can see the Gaussian blur does what it is intended to do, which blurs the image, basically taking an average of the nearest pixel values around it, and then it grayscales it, so maps the colors to black and white or any variation in between of gray. And then this edge detector basically uses a kernel, which in computer vision is like a matrix with different weights of the pixels around it, and you can use a certain values to be able to find edges in any image. So after the Hofflein P's method in OpenCV runs the algorithm on this frame of the image, it can be able to actually draw the yard lines, or in this example case, it will be for vertical lines of marchers. So that is what I'll show in this video here. Now, as the lines converge into the center, you can see the Yolo boundary boxes coming together, and the black line is the actual line drawn for the predicted vertical line, which is very accurate and uses those 4 computer vision algorithms to actually make the calculation. Another neat application of shape recognition in marching band drill is with respect to circles or ellipses, which use a linear algebra least squares model to take each marcher that it detects as a singular point, and then it basically calculates multiple matrix calculations in order to approximate the best ellipse, the best fit. So I will demonstrate that video again. The Yolo, the GUI could do all of this, but I've already processed all the videos here, so just for speed and time's sake. And as these marchers converge closer to the shape of an ellipse and more points are found, you can see the approximate ellipse being drawn on the video. Now, transitioning to a discussion of error correction, I needed to use more computer vision techniques to be able to find the yard lines and their respective numbers as well. So I will show the final Yolo annotations that were required for this process. Again, it's a lot of images, but given the time, the accuracy improvement is significant, and we can show the health check with all with the total number of annotations I had to complete for this project. So I will demonstrate an example output for this as well. This is an Ohio State marching band, and as the marchers clear out of the yard line numbers, you can see the algorithm is very accurate in determining which number it is actually detecting. And what I think is the most neat part of this video is that it can still find it when showing footage on the Jumbotron, or the big screen. Now, after I was able to find the yard line numbers, I wanted to know where the actual yard lines existed. So that is what this video will demonstrate. Again, it uses those 4 computer vision algorithms with the blur, grayscale, canny edge detector, and then the Hofflein's P method to be able to actually draw the lines themselves. So here's some example footage, and you can see, despite the probabilistic jumping of frames with some of the videos, most of them are very consistent in how accurate it can draw and detect these vertical yard lines. So that's what that video demonstrates, and then putting it all together, you could take the horizontal position of any marcher with their actual intended position to calculate the error of any marcher. Where this is an example drill sheet showing maybe what an intended drill sheet, their intended positions and coordinates would be. So already knowing the horizontal position, and then with future projects being able to detect the hash lines and hash markers to know the vertical component of their coordinate, you could combine these numbers and find the adjustment to actually improve the marching band drill. So I'll show what I was able to implement with the horizontal coordinate detection. So playing this video, you can see despite sometimes the frames being inconsistent, it is able to find the horizontal position. I'll find one frame in particular where you can see both the left and right 40 at one time being detected to see how accurate these are. Where the green represents the left 40, the blue the middle 50, and then the right, the red line being for the right 40, with these values being detected in between. Now, expanding upon this drill coordinate conversation, here's an example of one individual marcher's marching band drill sheet, and I wanted to make a way to be able to visualize this information more clear for maybe first year marchers, where you have these coordinates but you don't really understand what they mean. So you could take these PDF files or text files, which I'll show an example of here, and I created a program to be able to map out the progress of a given marcher, and that is what this final demonstration will be here. So here's the other GUI that I created. Again, it's with the tkinter Python library, and I'll run this find positions method to be able to plot out the progress and the path of a marcher over time. And if you wanted to know your position at any set, it can be displayed for you here as well. If any person wants to know the distance between any two sets, that can also be printed. And what I think is the most interesting aspect and helpful of this GUI is you can find your midway point or any other subset position between these two sets just calculated for you. So I can definitely imagine myself using this my freshman year if I was trying to improve the drill accuracy, and as the computer vision algorithms improve and you could know where a marcher is at any point, then being able to determine the consistency and how well they're actually mapping this position over time, you could be able to evaluate a lot about how accurately they are and give the adjustments recommended to actually improve this. So that's the last demonstration, and here's a little summary of that consistency calculator program where you can calculate the position, distance, or subsets. Now, my final piece of advice is to join the marching band. We're always looking for new people as well as crew, because I've enjoyed that as well. If you have any questions, you can email me here, and all the code is open source and up on my GitHub.